All right, we started this section last time, and we looked so far at the addition and subtraction algorithms within our normal base 10 system. We talked about some different ways of doing addition, different ways of doing subtraction. You probably thought some of them were interesting. You probably thought some of them were maybe more difficult than they were worth. But I wanted to show you some different options and how you can do addition and subtraction. So what we're going to do this time is we're going to actually start with those same addition and subtraction algorithms, and we're going to actually do them in other bases. So I have just a few examples of ones for other bases for us to take a look at maybe how our kids feel when they're adding and subtracting by making us feel a little bit uncomfortable about adding and subtracting, okay? So just a reminder, we're going to start with base 8. So in base 8, we have digits from 0 to 7, right? Everybody remembers that. So when we're looking at adding, in this case, 3, 4, base 8, and 1, 7, base 8, I'm going to do it in two different ways, okay, with two different methods. One of them is, you know, the one that you know and love and want to use because you're used to it, which is the standard algorithm. Oh, I forgot my stylus, just a sec. But I can try it. All right, so when we're adding in a standard algorithm, but this is in base 8, where do we start? What addition do we do first? The ones place, right. We would do 7 plus 4, right? And our number system, what is 7 plus 4? It's 11. But 11, of course, is not a single digit. And so even with ours, we would have to do some carrying involved, right, or regrouping. So, but in base 8, 11 is even more sort of not, if you will, a single digit. So in particular, we have this list above that says I go from 0 up to 7. What comes after 7 in base 8? 1, 0, and then 1, 1, 2, 3, 1, 4, 1, 5, and we keep going up till we get to 1, 7, and then we reset to 2, 0. So if I am adding 7 plus 4, so I'm starting with 7 and I'm increasing 4, where will that put me sort of on this line of numbers? It'll be 13, right? So this would be adding 1, this would be getting to 2, 3, and 4. I would be at 13, right? 1, 3. So I would actually write down a 3, and I would carry a 1. I'll explain one more way to think about that besides that one. But one way to do it is to simply write out the digits. That's very equivalent to what kids do when they count up on their fingers, right? Very similar. And then 1 plus 3 plus 1 is 5. So I have 5, 3, whoops, base 8. Okay, so that's one way. Let me talk a little bit another way of how I could get from 4 plus 7 to 1, 3. The other thing you could do is we already said that 4 plus 7 is 11, right? If I think about the number 11, how many, I don't want this to look like division, but if I were to regroup this, how many 8s are there in 11? There's 1, right? There's 1 8 in the number 11. And how many are there left over after the 8s? There's 3. So again, here's the 1 8. That's why I carried the 1 into that 8s column. And I have the 3 1s left over in the 1s column. Okay, another way to think about that. Okay, so that is the standard algorithm. Although it's not especially, I don't want to say especially useful, but it's not typically all that useful, the scratch addition. I wanted to show you another example of scratch addition after last time. So we're going to do scratch addition with this one. So if I were doing scratch addition, what we do is we scratch once we get to the number that the base is. So when we were doing scratch addition in base 10, as soon as we got to 10, we scratched and we remembered how many above 10 we were. So when we got, let's say we added together and we were at 12, we scratched, we forgot 10 of our digits and only remembered the 2, right? That's what scratch addition did. So if we were doing the same thing on this one, 4 plus 7's 11. right? So we have to forget 8 because we're in base 8, just like in base 10, we forgot 10. So we would scratch the 7 because that has exceeded our base 8, by how much? 3, right? 4 plus 7 is 11. That's 3 more than the base I'm working with. So that 3 is what gets written down. And then I scratched 1 time, so that was when the one we would regroup. 1 plus 3 plus 1 is 5. Make sure that when you're working with these, that you're writing the subscript down for the base. Okay? Let's try a subtraction problem. 3, 4 minus 1, 7. All right, standard algorithm. We're going to do the standard algorithm on all these because that's the one you think is the easiest, right? It's certainly efficient. I will definitely give you that. It's a very efficient method. Ones place. Cannot subtract 7 from 4. Agreed? So what would we do? We need to borrow or regroup, right? So we would borrow from the 8th place, and I would make the 3 a 2. I'm borrowing 1. But how many am I borrowing? 8. I'm not borrowing 10. I'm not in base 10. I borrow the base that I'm in. I borrow 8. So I'm borrowing 8, and I already have 4. So how many is that I'm going to have when I borrow 8? I have 12. Not 1, 4. It's the number 1, 4, but it's 12 as a single value. Okay? It's kind of, we do this in ours too. Like we write a 2-digit number in this 1-digit spot. Okay? So it's the same idea. I've borrowed 8, I already have 4, I have 12. So then I can subtract like I would have liked to have done to begin with. 12 minus 7 is 5. 2 minus 1 is 1. Base 8. So the other one I want to do for you is equal additions. Now equal additions is the one I told you last time that the whole point is not to borrow. No borrowing. Okay? So I have 3, 4 minus 1, 7. I want the 7 to become a 0. Right? That's what I really want. I want whatever is on bottom that's sort of causing my problem in subtraction to turn into a 0. So what would I have to add to 7 to get it to become a 0 in base 8? 1. Right? 7 plus 1 would be 8, and in base 8 that becomes the digit 1, 0. But if I add 1 to the bottom, I have to add 1 to the top. So 3, 4 becomes 3, 5. 1, 7 actually becomes 2, 0. Right? The next digit after 1, 7 is 2, 0. And then if I subtract, I have the 1, 5. Just like that. It's actually a very quick problem on that one to do equal additions. Okay, so when you do these problems, you're just going to do them once. I'm just showing you alternate methods because some of the times they ask you to do a specific method, and some of the times they just let you choose your method, okay? That's why I'm doing what I'm doing. All right, let's try one with addition again in base 3. So we're going to look in base 3 now. Base 3, man, that's a small base. There's only 3 digits, right? 3 numerals, I should say. 0, 1, and 2. That's all we have. So our digits 0, 1, and 2. And I'm supposed to add together lots of 1s and 2s. I have 1, 2, 1, 2 plus 1, 1, 2. And just like I did a moment ago, we're gonna use our standard algorithm. So we start in the 1s place. What is 2 plus 2? Well, it's 4, but that's too big for our base, right? So if I'm thinking of it, you can do it a couple of ways, right? You could write out some more digits. What comes after 2? 1, 0, and then 1, 1, and then 1, 2. That's actually far enough. So you could do that. We could count up. So if I have 2 plus 2, I would be at 2, and I would count up 2 from that. That puts me at 1, 1. Or you can say I've got the number 4. How many 3s are in 4? 1. So I carry 1 3. And how many is left over? 1. So I write the 1 in the ones column. So now that I'm in the threes column, I've got 1, 1, 1, which is a total of 3. But how do you write 3 in base 3? 1, 0. So we carry a 1 and we write the 0 in the threes column. Now I'm in the 3 squareds column, or the nines column. 1 plus 2 plus 1 is 4, right? Which is 1, 1. So I carry a 1 and I write a 1. And then I've got my 3 cubed column, or the 27s column, and 1 plus 1 is 2. So 2, 1, 0, 1, base 3. Okay, so let's add this one now in the lattice method, okay? So the lattice, remember, if it's up to a 4-digit number, you need 4 spaces for your digits. That's super unbalanced. Let me try that again. Problem is I need to shift it. That's so much better. Okay, and you split the back boxes along the diagonal. And it doesn't matter whether you add left to right or right to left, so just for fun, we'll add from left to right. So in the first row, or in the first column, I would just have a 1. My second column, I have the number 2 plus 1, numbers 2 plus 1, which is 3. But how do I write a 3 in base 3? 1, 0. And then I have a 1, 1, that's 2. And then a 2, 2 we've written as 2 plus 2 is 1, 1. Okay. So once I have sort of the lattice filled in, or the grid filled in, I add along diagonals. And I do need to start in the bottom right-hand corner. So that's a 1. And then 2 plus 1 is 1, 0. So I'll write my 0, carry my 1. I have 1 plus 0 is 1, and 1 plus 1 is 2. So 2, 1, 0, 1, base 3. Okay. One more example in base 3. Oh, looks like it didn't get cleaned off from last time. Well, let's just clean it off real quick. The rest of them did, just one got missed. Okay. So we have 1, 0, 0, 2, base 3, minus 1, 1, 0. All right, in the ones column, I'm good to go. 2. But the next 2 columns both have lots of zeros in them, right? So I have to go to the far right to borrow, because there's no more numbers until I get all the way over to the 1 in the far right. So when I borrow 1, this one becomes a 0. But when I borrow in base 3, I borrow 3. So there's now a 3 here that I have added into that column. But I need to borrow from it for the next column over, right? So I borrow 1, so it becomes a 2. And when I borrow in base 3, I borrow 3. So now I have a 3 in my threes column. Subtracting threes column, I have 3 minus 1, which gives me 2. And then I have 2 minus 1 as I move to the left, and 2 minus 1 would give me 1. So this is 1, 2, 2, base 3. Don't go with the next page just yet. We're going to do one more method. So we're going to look at the, excuse me, the equal additions method one more time. All right, so as we already said, it works just fine in the ones column. I don't need to worry about the ones column. But what would I have to add to the threes column, you know, the second column from the right, to get that 1 to turn into a 0? My goal is always to make zeros. So what would I have to add here to turn that 1 into a 0? 2. And a 2 in the threes column, right? So it would be 2, 0. So I'm going to add 2, 0 to the top and bottom. So now I have 1, 0, 2, 2, oops, minus what? 2, 0, 0, right. The 2, when added where I've drawn my arrow, will make that become a 0 and carry a 1 over. So now I have 2, 0, 0. But I still got a problem, right? It's just been sort of pushed one direction to the side. Now I can't do that column either. I have a 0 minus 2 happening right here. So what would I have to add to that 2 to get it to become a 0? I'd need a 1, right? 1 what? Yeah, 1, 0, 0. So on the top, that just makes 1, 1, 2, 2. On the bottom, what does that give me? Yeah, I get the number 1, 0, 0, 0. And subtraction is very nice here because there's no borrowing. So what do I get when I subtract these two? 1, 2, 2, base 3. Okay, you ready to switch gears? We're going to do some mental math and some estimation. The first thing that I want to make sure that everybody is aware of is that the phrase mental math does not mean estimate. Okay, mental math just means doing the math in your head. All right? Estimation is something different, and sometimes estimation is done in your head, right? Yeah, sometimes estimation is done on paper, but estimation and mental math are not the same thing. So we'll start here by using mental math, and we're going to add from left to right. So I'm just going to show you a variety of mental math strategies. Here's the catch. When you're doing mental math, as much as you might wish it were true, or maybe not wish it were true, I can't see the math in your head. So you have to write down for me what's going on in your head so that I can see what you're thinking. Does that make sense? Okay, so while this is mental math, we are going to write it all down. Are you with me? Okay, so I've got 46 and 38. So what addition from left to right means, I'll write it as a in a vertical format, is that instead of adding, from right to left like we normally do, we add this piece together first. So in essence, what we're really doing is we're adding 40 plus 30 to start with. So 40 plus 30 is what? It's 70. And then I add the other column, 6 plus 8. 6 plus 8 is 14. And then I add the results together. What is 70 plus 14? 84. And the idea is, especially if they are just two-digit numbers, is that you can keep track of that much information for that short period of time and then combine the sums when you're done. Okay? And it's very helpful because when you're adding the tens digit, you automatically get a multiple of 10, right? Like 30 plus 40 is not 46. Right? You don't get a 0 in the ones column, and that makes the addition easier in a moment. So this is addition from left to right. Breaking up and bridging is a really cool one. So breaking up and bridging looks like this. You take the 46, or whichever number's first, doesn't matter really, but you take one of the numbers, and you add the number to it, but you only add the tens digit. So like 30. I can add 46 and 30 together in my head, almost as easy as 4 and 3, because there's a 0 in one of the places, which means I don't really have to do anything. So what is 46 plus 30? It's 76. And then the piece that I didn't have, that 8, gets added on at the end. So this is the breaking up part. I've broken, well, I should say it this way. This is the breaking up part, 38. And the bridging is adding them together piece by piece. So 76 plus 8, again, it's almost single-digit addition, right? 8 and 6 is 14, so I get 84. All right. The next one, trading off, is very similar to what I do when I work my budget every month. It's got to all add up to the money I have coming in. So if I add money to the Christmas fund, I have to take away from the money that I was going to spend on clothes this month or whatever. There's got to be a balance going on. It's all about balance. So the trading off method is about balance as well. So when we were doing equal additions, which is a subtraction algorithm, the idea was to get something to become 0 to make the subtraction easy, right? Well, trading off has the same idea. The idea is to get something to be 0 so it makes the addition easy. So either you can take the 6 on top and turn it into a 0, or you can take the 8 on bottom and turn it into the 0. And in this case, one of them is closer to 0 than the other one. Which one's closer? The 8 is. Because I can add 2 to 38 to make it 40, right? Now, when we were doing equal additions, if we added 2 to the bottom number, we had to add 2 to the top number. But this isn't subtraction, this is addition. So if I add 2 to an addition problem, I also have to subtract 2 from an addition problem in order to balance it, right? If I add money to the car fund, I have to take away money from the trips fund or whatever it is I'm balancing in my checkbook. So I'm going to subtract 2 from my, in this case, my top number. So 46 minus 2 would be 44. And so I end up with 84 from that perspective. It's all about balancing, adding a piece, subtracting a piece. All right, our next one is called compatible numbers. Compatible numbers is all about recognizing that some numbers are easier to add together than others. For example, 40 and 60 are easy to add together. Why? Because I get 4 and 6 equaling a 10, right? So 40 and 60 are nice to add together. They are compatible because they equal 100. Any others that you see that are like that here? Yeah, 30 and 70. 30 and 70 are nice to add together because they also equal 100. I have the lone guy 50 in the middle for a grand total of 250. So if you don't have compatible numbers, but they're like almost compatible, that's our next strategy. You can make compatible numbers. So if you take a look at 35 and 68, they're not compatible. They're close. If I could just adjust one of them a little bit, they'd be compatible. I'm going to leave my 35 alone. What number would be close to 68, but nicer to add to 35? 65 is the one we usually go with. 70 would be okay. You could do that if you'd like. 65 is nice because this ends up equaling 100, right? But again, you can't just change the 68 to a 65. If you do, that's estimation. So what would you have to do? You need to add 3 still, right? You're missing it. I mean, that value of it. So this would be then 100 plus 3, or 103. Cameron, if you decide to go up to 70, that's okay. So if you were to do this and you were to say 35 plus 70 because you like the 7 and the 3, right? You've increased it by 2, right? So you'd also have to decrease by 2 over here. So you'd end up with 105 minus 2 for 103. Okay, everybody good with that? Okay, breaking up and bridging. This is breaking up and bridging, but with subtraction. We did breaking up and bridging a minute ago with addition. Works the same way. So what we're doing, instead of actually subtracting 46 minus 38, is we're breaking the 38 up into 30 and 8, and we're doing it piece at a time. So we start with the 30. What is 46 minus 30? 16. And then I do the 16 minus the 8 to give me 8. So breaking it apart into 2 steps is often easier than doing it in 1 step, depending on what values you're working with. All right, we also have trading off with mental math, but the reality is that trading off with this description is exactly the same as equal additions. So we'll have another practice at it, but this is just equal additions. Remember, the goal is to get the subtraction value on the bottom. In this case, we're talking about this number here. The goal is to get it to be 0. So what would I have to do to get the 38 to be 0? Plus 2. And because it's subtraction, I would also have to do a plus 2 on top. So 46 plus 2 would be 48. 38 plus 2 would be 40. And then if I subtract, I get 8. All right, one more mental math strategy. This is called dropping the zeros. Again, not every strategy works for every numbers, but when they work, they're nice. I have lots of zeros on this, right? And we all know that 0 doesn't really have a lot of impact on our value when we're operating on it. It impacts the answers, but it doesn't impact the operation. So the idea for the dropping the zero strategy is to only report the items that are non-zeros or in columns that are not completely zeros. So if I had 46 minus 34, because it's 4600 minus 3400, what would 46 minus 34 be? 12. But I dropped 2 zeros, right? So my answer is 1200. All right, the last set of questions that we're going to look at are going to be computation estimation. Okay, so everything we did before was mental math, exact answers, but in our head, we're only writing them down so that I can see the inside of your head, okay? Everything after this is going to be approximations, which means that there may be more than one answer that's actually appropriate depending on how you are approximating, all right? There's not one and only one answer on these necessarily. This first one we call front-end estimation with adjustment. So front-end estimation is the idea that whatever your leading term is, your leading digit, we operate with only those to start with, okay? So the 3 here is equivalent to 300, the 4 here is equivalent to 400, and the 2 at the end is equivalent to 200. I just zero everything out, okay? Ignore everything else. So 300 plus 400 plus 200 would be 900. Okay, so this is, sort of, this is the front end part. Actually, I'll write it out there. The adjustment part is all about compatible numbers. So remember, compatible numbers were numbers that we were trying to get to add together nicely. So right now, the adjustment part is 32, 62, and 25. And this is estimation, which means I'm looking for 2 numbers that I can combine to something that's approximately nice. Are there 2 of these 3 numbers that are approximately nice when added? Oops. Yeah, these 2. 32 and 62 are approximately what? They're approximately 100. All right, this is approximation, estimation, not looking for exact answers. This is about 100, right? 30-something and 60-something is about 100. So if I were to combine the 900, the 100 because it was compatible, or nearly compatible, and the extra 25 over here, what would my total be? 1,000 to 25. Yes, ma'am?
Does it not matter that the 462 is closer to 500?
Nope, not for front-end estimation. Because you're compensating because you're putting this over here. Right? I mean, yeah, so that's why. Yeah, it doesn't make any difference whether the number is closer to, it's not rounding. It's not rounding up, it's not rounding down. It's actually something that's also called rounding off. Rounding off means you take the first digit and ignore the rest. It's another way of describing it. Okay, grouping to nice numbers. Okay, so again, this is like compatible numbers. So this is an approximate compatible numbers. That's what we're looking for. So your 2 that you'd combine and say that they're about 100 or whatever may not necessarily be mine. So somebody give me 2 numbers that you say, when I combine them, they're pretty close to 100. 35 and 65. 55. What is 65? That one? All right, so those 2 are about 100. Sure. What else? The 42 and the 55, those also are about 100. And then I have the 71 left. We'll just round it off, so we've got 270. if you leave it as 271, it feels an awful lot more like you're being specific. You know what I mean? It's like having the conversation in the car, and one of my children asks me, what time is it? And I always round. It's 3:15. Nuh-uh, it's 3:16, Mom. Okay, great. We don't need to be that specific, okay? This is estimation. Okay, we have another one. This is one of my, I don't want to say it's my favorite one, but when it works, it's really nice. Clustering only works when the numbers are all sort of close to the same number to begin with. So obviously not going to work all the time. But if the numbers are sort of bunching up somewhere, it will. So if you take a look at all of these numbers, what are they all pretty close to? They're all pretty close to 500. So this is approximately equal, right, to 500 times how many numbers? 5. And what is 500 times 5? 2,500. Yeah. It's about 2,500. I didn't even have to add, right? I'm supposed to be adding. I didn't even have to add because it's compatible or because it's clustering. Okay, Brooke, you mentioned the idea of rounding. You didn't use the word, but I did. Rounding is our next one. With rounding, sometimes, I mean, when you're in a contrived situation, right, like a textbook, sometimes it will tell you round to the nearest 100, right? This particular set of problems, for the most part, doesn't tell you how to round. It just says round, which means you have to decide where you want to round it to. And depending on the context might sort of drive your decision. You know, do I need to round it to the hundreds place, or is the thousands place sufficient, or whatever? So we'll just do a couple of examples, but when it says to round, most of the time, unless it tells you, you're going to pick to what value, or to what place value, I should say. So the easiest place value to pick with this problem would be what? The thousands, because I'm going to get the most zeros. I mean, that's what it is. So if you'll remember the way that you round, we'll use the first number here. The thousands place would be my first place value. And you look at the number in the place value to its right. If that number is 5 and up, then you round the 4 up to a 5, and you make everything else 0. If that number, like it is over on this one, and I'm rounding to the 3, if that number is 0 to 4, you round down. Rounding down means that the 3 stays a 3, and all the others become 0. So my answer when I round this number is either going to be 3,000 or 4,000. When I round this one, it's either going to be 4,000 or 5,000. Okay, I can't round it to 3,000. I'm not going to change the 4 down to a 3. That's never going to happen. So if I'm doing this to the thousands place, the first one is a 5,000, and the second one is a 3,000, for a total of 8,000. That would be rounding to the thousands place. But maybe you feel like, or the context suggests that maybe that the hundreds place would be better. So let's try the process again with the hundreds place just to see an alternate example. So if I'm looking at this number, what number is in the hundreds place? The 7. So either the 7 is going to stay a 7 or it's going to go up to an 8. Those are the only two options. The 4 before it's going to stay regardless. In order to decide on the 7, I need to look to the place to the right, the 8. Is the 7 going to stay a 7 or is it going to round up? It's going to round up. So I'm going to have 4,800. On the second one, that's my hundreds place. It's a 1. I'm going to look at the 4. Am I going to round the 1 up to 2 or is it going to stay a 1? It's going to stay a 1. So I have 3,100. And then I would add, in this case, 7,900. Notice your answers are similar, right? They should be. I mean, they're not going to be crazy far off because you're using the same kind of patterning of number rules or rounding rules as you're working. The last one is perhaps the most flexible, but maybe gives you the best picture of what's going on. It's called using the range. The range means being able to say at the end, well, the answer's between this and this. That's what a range is. It gives you a range of values where your answer is between. Okay? So here's how it works. You take the first digits and you just round them off. 300, 600. That's 900. You take those first digits and you round them up. 400, 700, 1100. So my range is 900 to 1100. The answer's somewhere in between. And oftentimes that's sufficient information depending on what you're working with. We work with a mission organization in Ethiopia and they send us budgeting information. If they can give me kind of a range of where their food costs are going to fall, then we know what to expect, right? I don't really need to know the exact amount. I need to know some kind of approximation, and a range is a good way to do that. All right.